In this video, we build the starting structure for the transition state optimization for intermolecular protonation involving the N-carbon atoms. We begin by selecting and adding the divalent carbon fragment to the view window. After repositioning, add carbon atoms to each open bond. Then, modify the right bond type to be resonant. When we clean the structure, this bond length will increase slightly. Next, add hydrogen atoms to the N-carbons, 3 on the right and 2 on the left. We now need to adjust the relative positions of the hydrogen atoms in the 2 ends of the molecule. Reposition the molecule in the window and then modify the HCC-H dihedral angle. We've now finished the basic unit, which needs to be duplicated. We reposition the molecule in the window to make room for a second instance. We select all the atoms in the molecule and then choose Edit, Copy. When you have copied a structure to the clipboard, you can add it to the current view by simply clicking with the mouse button, which we do now. Hold down the Alt key to have the mouse affect only the new fragment rather than the entire molecule. Next, reposition a new fragment in order to join it to the previous one, rotating about 2 of the 3 axes. Then, move it into position with respect to the other fragment, allowing the 2 relative hydrogen atoms to overlap. Then, delete those 2 hydrogen atoms and add a bond between the remaining 2 carbon atoms. The structure is reasonably close to the one we want. We use the point group symmetry feature to refine it. After opening the dialog, enable symmetry. The current point group is C1, and we would like it to be C2H. We can use the controls in the middle section of this dialog to symmetrize the structure. The pop-up on the left lists the higher point groups which Gauss View is able to apply to the current structure. Here, it is empty, but we can loosen the symmetry tolerance to make more choices available. After doing so, select C2H and click the Symmetrize button. Our next step is to add the hydrogen atom at a point midway between the 2 structures. We remove the bond that we added between the 2 fragments and increase the carbon distance to about 2.8 angstroms. Then, choose the hydrogen atom in the Element Fragments panel.
Finally, right-click in the View window and select Place Fragment at the centroid of selected atoms from the Builder menu. Then add half bonds from that hydrogen atom to each of the carbon atoms.
Now check the symmetry of the molecule, reimposing C2H symmetry if necessary. We will do this after each modification from now on. Turn on symmetry constraints and enable ongoing tracking of the point group symmetry. The last step is to change all of the hydrogen atoms within the fragment to methyl groups. Select the tetrahedral carbon from the elements fragment and then click on one of the outer hydrogen atoms in the upper fragment. A methyl group is added there and simultaneously at the symmetry correspondent location in the other fragment. Repeat the process for the other exterior hydrogen atom and then for the 4 hydrogen atoms closest to the centroid hydrogen. The latter are all modified in a single step by symmetry. Once the molecule is complete, a final trip to the point group symmetry dialog indicates that we will need to reimpose the desired C2H symmetry. After doing so, the starting structure is now complete.